Alright, so what I want to talk about now is finding the equilibrium constant when we are given a problem or we actually have a solution in lab or a reaction in lab. So the way we do this is by using an ICE table, and these are kind of famous in the AP world, the Gen Chem world. We're going to use them a lot. So an ICE table is a way to organize the concentrations. I stands for initial, as in initial concentration. C stands for change in concentration, and E stands for the concentration at equilibrium. So what we have here, this part right here is kind of like a problem. So suppose that we have an initial concentration of this reaction here where A is 1 molar and B is 0 molar. So in my ICE table, which I don't usually write out initial change in equilibrium, I just put ICE, we put 1 for the initial concentration of A and 0 for the initial concentration of B. And then it says at equilibrium, the concentration of A is 0.75. So I plug that in. Okay, so these numbers, we don't have them yet. All right, that's unknown to us. So our table would look like that. Well, since we know that A changed by losing 0.25 molarity, we can assume the stoichiometric ratio that if we lose 0.25 moles of A, we're going to make twice that of B. So B is starting at 0, and what we do is we add 2 times 0.25 here to give us 0.5 at equilibrium, and then, of course, the equilibrium concentration is 0.75. To calculate K at that point, it's very easy. K is equal to products over reactants raised to the coefficient. So the concentration of the product B is 0.5 squared. The concentration of A is 0.75, and it's raised to the first power. And then that's all you would do. So look at this example. You have carbon monoxide and hydrogen going to CH3OH, a little methanol there. You have it at 780 degrees Celsius. That does not matter other than the fact that, as we'll learn later, the equilibrium constants change at different temperatures. So we have an initial concentration of carbon monoxide of 0.5 and hydrogen of 1. Now look at this. It does not give you the concentration of the methanol. So in this case, if it doesn't do that, just assume it to be 0. So I'm going to go ahead and make my ICE table. I have my carbon monoxide, and I have my hydrogen, and then I have my methanol. Alright, so then I would just go I, C, E, and then I make my little columns like that, and then I would just plug in 0.5 here, 1.00 here, and 0 there, and that's how we would start. Then it says the carbon monoxide concentration at equilibrium is found to be 0.15. So you plug in everything you know, and then from there you work on it. So I'm going to go to the next slide. This is what it would look like, nice and cleaned up without my bad handwriting. So now what you have to do is figure out how much the carbon monoxide changed over the course of the reaction. Well, it would be losing 0.35 molarity. Well, if we look back at the reaction, you have a 1 there, a 2 there, and a 1 there. So it's a 1 to 2 to 1. So if it helps you, sometimes I put the mole ratios up here. Alright? So if 0.35 was lost by carbon monoxide, now this is the difference between the products and reactants, we're going to lose 2 times that amount for hydrogen, and we're going to gain that amount for CH3OH. Does that make sense? Hopefully it does. You can't answer me because this is a video. So that's what we get. Now all you got to do is the math. So if you subtract 70 from that, because 2 times 0.35 is 70, you get 0.3 left over. And then 0 plus 0.35 is 0.35. So since it was a 1, 2, and 1, and this over here was our product, the K value is going to be equal to 0.35 over 0.15 times 0.30 squared. And that is really all there is to it. Not too shabby, huh? Should get Kc is equal to 26. So hopefully that makes sense, and we'll start talking about something else next video.